Here we want to show that if we have a set of n linearly dependent non-zero vectors, then we can find at least one vector that can be written as a unique linear combination of the vectors before it. We'll do this by constructing a set such that this situation holds. So let's look at the solution. So we're going to start with one vector in a set. So let S1 equal just the vector V1. This set is linearly independent because none of the VI's are the zero vector. Now let's add to the set. So let S2 equal V1 plus another vector V2. If S2 is linearly dependent, then we're done, because then V2 is equal to some constant times V1, so we've written one vector as a linear combination of the previous ones. If not, then we continue adding to the set. So we let S3 be the set of V1, V2, V3. And again, if S3 is linearly dependent, then we're done for the same reasons. Again, if not, we continue to add to the set. Eventually, we'll get a set S sub k to equal the set of V1 to Vk, where this is now linearly dependent. And the set V1 to Vk minus 1 is linearly independent. Otherwise, we would have stopped our construction earlier. So this new set S sub k is linearly dependent only by adding the new vector V sub k, which means that V sub k is in the span of the vectors before it, or we can write it as a linear combination. So V sub k equals A1 V1 up to AK minus 1 VK minus 1 for some AI real numbers. And at least one A sub I does not equal 0, otherwise V sub k would be the zero vector. Now let's show uniqueness. So we suppose that there's another linear combination of V sub k with the vectors before it. So we'll choose B1 V1 plus BK minus 1 VK minus 1, and your BI's are real numbers. Then subtracting the two linear combinations, we get that the zero vector is equal to A1 minus B1 V sub 1 plus up to AK minus 1 minus BK minus 1 VK minus 1. But since the V1 to Vk minus 1 vectors are linearly independent, it means that the coefficients AI minus BI necessarily equals 0, which means that AI equals BI for all I. So we cannot write V sub k as two different linear combinations of the vectors before it, and hence uniqueness.